Welcome to the second part of the problem-solving session for Chapter 33. We begin where we left off with question 6. Here, we're given a series RCL circuit that has a resistor of 425 ohms, a capacitor of 3.5 microfarads. Notice that that appears to be an M. That's because this software doesn't differentiate Greek from Roman. So this is an actual micro, and you recall micro is e to the minus 6. So this is e to the minus 6 farad for microfarad. And the inductor has a value of 1.25 Henry. The frequency of the generator has been given to us as 60 Hertz, and we're told that the maximum voltage from the generator, this is a delta, is delta V max 170 volts. And we're asked to determine the following quantities. The angular speed of the generator, omega, well, let's call this part A. Omega is related to the frequency of the generator by 2 pi times f. So when we take 2 pi times 60 Hertz, we get 120 pi radians per second. And 120 pi radians per second, if we put the pi as, if we strike the key on our calculators of pi, which is 3.14, etc., we get a value of 377 radians per second. So this is our value of omega. Next question asks us to calculate the capacitive reactance, the inductive reactance, and the impedance, or the total reactance in the circuit. Well, let's begin individually. X sub c is 1 over omega times c, and since we have our value for omega, let's go ahead and plug in 1 divided by 377 radians per second, multiply that by c, 3.5 e to the minus 6 farad, and that gives us an X sub c value equal to 758 ohms. X sub L, on the other hand, is omega L. Again, our omega is 377 radians per second. Our L was given to us as 1.25 Henry. Multiplying it out, we get a value of X sub C, which is equal to 471 ohms. Z, the impedance, is the square root of R squared, 425 ohms squared, plus X sub C, 700, is it X sub L minus X sub C? I believe it's X sub L minus X sub C. So 471 minus 758 squared, and of course that's going to be ohms squared, and when we plug this into our calculators, we get a value of the impedance, Z, as 513 ohms. Next question asks us to determine the maximum current through the circuit, and here what we're going to do is use Ohm's law, but we're going to use delta V max total, what was given to us as the coming out of the generator. And because we're using the total as opposed to R, C, or L, we have to use the total reactance, which we call the impedance. 170 volts is the maximum, divided by 513 ohms, what we just found. And that gives us a maximum current through the circuit, which is 0.331 amps. Next, we're asked to calculate the phase angle, phi, which is given by the inverse tangent of, and it's going to be X sub L minus X sub C, 471, minus 758, divided by R, 425. Of course, the unit ohms is going to cancel throughout. And here we see that we get a negative phase angle. Well, that's absolutely fine. That just confirms that X sub L is a number smaller than X sub C. Next, we're asked to get the maximum voltages across each of the circuit devices. So let's begin with delta V through the resistor max. Well, we get this using Ohm's law, I max, but we multiply that by R since we are restricted to simply that of the resistor. 0.331 amps times, remember this is series, so that all circuit components get the same value of current. 425 ohms gives us 140 volts. Next, delta VC max, and here we have to use Ohm's law, but we must restrict ourselves to X sub C since we only want the voltage across the capacitor. 0.331 amps times 758 ohms gives us a value of 251 volt. Delta VL max, I max times X sub L, 0.331 amps times 471 ohms gives us a value of 156 volts. Then the second part of this question asks us to determine the instantaneous values. Well, these are the values as a function of time. Delta V sub little v, see, delta sub little v sub R is given by delta V R max, 140 volts, times the sine of omega t, but omega was 377 times t. So as a function of t, we need to have a t in there. Delta V sub c, we get the maximum 251 volts, and we can either write this as minus cosine of 377t, but recall that minus cosine of 377t is also equal to the sine of omega t, 377t, minus pi over 2. So either 251 times the cosine of 377t or times the sine of 377t minus pi over 2. Delta V sub L, maximum 156 volts, this time either times positive cosine of 377t or the equivalent of that, and this is a positive here, sine of 377t, this time plus pi over 2. So we have a choice of how we want to express the time-dependent voltage. Next, we're asked to calculate the power factor. That's the last, actually it's not quite the last part, but I'm running out of room here. So I think I'm going to have to go up and find a little bit of empty space there. The cosine of phi, well, of course, phi is minus 34 degrees, so the cosine of minus 34 degrees is equal to 0.829. That is the power factor. Last, we're asked to calculate the average power consumed in the circuit. So I'm just going to look for a little bit of empty space, which I'm not finding. Let's just do it here then. The average power consumed in the circuit, we can either get that by taking the RMS current, squaring it and multiplying it by R, or we can get that by getting the RMS current times delta VR RMS. In any case, IRMS is, of course, The maximum, which we found earlier, was 0.331 amps, divided by, oops, our letters are our numbers are not looking too well, divided by the square root of 2, and when we plug in the numbers, I've run out of room, so I'll just write down the result, and you can double check that you get this. I get 23.2 watts as the average power consumed in the circuit. So you can get this within rounding. There may be a rounding error here, but within the rounding, whether you use this expression for average power or this expression for average power, be sure though that if you use this one, that you use delta V sub R RMS, because after all, remember that power is only consumed in the resistor. Okay, next question, and it appears to be our last question. Here we are told that we have an RLC circuit of a resistor of 20 ohms, a capacitor of 100 nanofarads. What is the nano? The nano is 10 to the minus 9, which means that this is e to the minus 9 farads. The inductor is 20 millihenries. Milli is 10 to the minus 3, which is the same as e to the minus 3. And the generator supplies a voltage, time-dependent voltage, which has a maximum delta V max, and this is of course total because it's the generator, times the sine of omega t. The first question is, what is the resonant angular frequency omega naught? Well, here, in order to determine omega naught, we have to ask ourselves under what condition do we get resonance in the circuit? And of course the answer is when x sub L is equal to x sub C, of course. That means omega at resonance, omega naught, times L must equal 1 over omega at resonance times C. Well, you can see that if we take omega and we multiply both sides by omega, so we cancel it out on the right, we end up with omega squared equals 1 over LC. And of course, if we square root both sides, then we get omega at resonance is 1 over the square root of LC. Well, plugging in our values, we had a value of L given to us as 20, e to the minus 3 Henry, and a capacitance of 100 e to the minus 9 farad. When we carry out the calculation, we find that omega at resonance is quite a big number, 22,360 radians per second. We're asked to determine next the maximum value of the current at resonance. In other words, when the current is at its largest value, is at a maximum, because, and not just maximum in the terms of amplitude, but maximum because Z is at its minimum. And if you recall, because of the condition that x sub L is equal to x sub C, x sub L minus x sub C is 0. That means that Z at resonance is just equal to R. Well, in this problem, R is equal to 20 ohms. So to get I at resonance, we use delta V max total divided by Z at resonance, and that gives us 100 volts divided by 20 ohms, which gives us a very large current of 5 amps. So that's our I maximum at a maximized value because of resonance. And the last part asks us to determine the maximum voltage through the inductor at resonance. Well, of course, that's going to be I max at resonance times X sub L at resonance. Well, we just got the value of I max at resonance, which is 5 amps, and to get X sub L at resonance, it's omega at resonance times L. Well, omega at resonance was this huge value of 22,360 radians per second. Multiply that by L, which is 20 e to the minus 3 Henry, and that gives us a value of 2,240 volts. But of course, delta V max sub L at resonance should be the same as delta V max sub C at resonance. Why? Well, using Ohm's law, I max at resonance times X sub C at resonance. And don't forget that the condition for resonance is that X sub L equals X sub C. Since we are multiplying X sub L or X sub C by 5 amps, we should get the same voltage, which cancels out, obviously, 2,240 volts, canceling out the effect, because remember, it's one minus the other. Since they are equal, then essentially the capacitor and the inductor have basically canceled themselves out. Well, this concludes the last part of Chapter 33 problem solving session. Until next time.